Hi, welcome back. Again, my name is Orlando, and in this video, we're gonna review the simple exponential smoothing method, and we're gonna see how to implement it in R. So just to briefly review, remember that the simple exponential smoothing method, the idea is to, instead of using an equally weighted sum of the past whatever values of your demand time series, you can instead take sort of a weighted sum where the older values are going to weigh a lot less than the most recent ones. So to do that, you can use this expression. So the estimated level at time t plus 1 is going to be what they call a convex combination of the current observation, so the current demand. So t plus 1 is now sort of the present, and t is sort of the past now. So the estimated level at t right now is sort of a convex combination of the demand right now and the previous estimate of the level. Okay, so if you actually work out this expression, then you get this this final sort of expression for the estimated level, where as you can see, the weights for the levels start to decrease as as you go back, as you go further in the past, and that's because alpha is a value from 0 to 1, is a constant, so it's a parameter that you need to introduce, and 1 minus alpha is also in the interval from 0 to 1, because alpha is from 0 to 1, and therefore once you take the square, the cube, and so on, this value is going to decrease more and more and more. So these are sort of the weights for the demand. So this is a weighted sum, and the weights are sort of starting to decrease as you go further and further into the past. So the idea here is that the older data points are, in a sense, less relevant today or right now. Okay, so formally, this method will look like this. So this is the estimate of the of the level, and then the forecast is exactly as it was before. So you estimate the level right now, and then you forecast the future, the immediate future, as the current estimate of the level. And much like the moving average, this method is especially suited for stationary series, so time series with no trend or seasonality components. Okay, so let's go into R, and like before, Professor Pazur provided you guys with some R code. So let's use that first. So we're gonna run the same library as before. Let's load the same data set as before, the King's data, make it into a time series, and then we're going to use this function hot winters, okay, which is a particular implementation of the simple exponential smoothing algorithm. So we need to fix these values beta and gamma to false. They're going to be, their meaning is going to be clear in the future, but for now just set them to false. And here L starts is your L0. Oh yeah, I forgot to mention. So here you need to specify your alpha, which you call the smoothing constant, and you need to specify the estimate at time 0, so the initial estimate. So, and that's because the estimated level at time 1, so at the first instance of time, is going to be a convex combination of the current, so the demand at time 1 and the estimated level at time 0, so which you cannot estimate it, so you need to provide it somehow. So there are some suggestions in the seen in class and in the book, so you can fix it to be the initial demand, so D1, or you can take it to be the average of all the demands, although that can introduce some bias. So here you're going to use L start, so this is L0 as 60, which 60 is actually King's 1. It's the first data point. So we could instead we could actually replace this by King's 1, which is what it is meant. So we're going to run this. So the output is here, is the smoothed version of the King's dataset. So let's see how it looks like. If we print this, it does not immediately give us the smoothed values. Instead, it gives us this with some information regarding the parameters. So beta and gamma are not relevant here. Alpha, if you noticed, alpha is also a parameter here, and when you do not introduce alpha into the Holt-Winters function in R, in this package, it will automatically compute the alpha, whatever that alpha is, that minimizes the mean square error. So it will choose sort of the optimal value for alpha, unless you want to insist on some other value of alpha. So if you want to force it to be something else, you can. But typically you want it to be an optimal value, of course. Okay, so if you want to actually extract the smoothed, so the estimated levels, you can, so let's delete this first. You can run this fitted section column, let's say, of this data set, and you're going to run it, and you're going to obtain this this sort of table, and here you have the estimates of the level. I'm sorry, this second column, and these are the forecasts. Okay, so let me remove this, and you can now use also this command to obtain the sum of square errors, which is not exactly the same as the mean square error. So it's the mean square error, MSE, is actually the sum of square errors divided by the length of your data set. Oops. So this is actually the MSE, the mean square error. So if we wanted to compute this, then MSE is this value. Okay. Now let's plot this to see how it looks like, and it will, for this function, will automatically plot both your smoothed time series and the original time series. So it will superimpose, so you can more easily compare the two. And as you can see, it is sort of smoother compared to before. Okay. Now you can also forecast using this library forecast. Again, if you do not have it installed, you can go ahead and install it. And you can now, for kind of technical reasons, to use this function Holt-Winters forecast, you need to use this kind of ugly notation. This is what we call a namespace, because there are some conflicts in the name of this function, but let's not go too much into those details. So to use this function, it just basically replicate this, what you see over here, and let's run it. So this h equals 8 so we will compute the next 8 estimates, the next 8 forecasts, I mean, from the final demand, from the final observation in your data set. And we ran it already, so let's see how it looks like. And as you can see, the forecasts are all the same, and that's because, remember, that we had, so this is the older one. Remember that the forecast into the immediate future is going to be your estimated level now, and the forecast into all the future based on the data you have now are always going to be the same. You're always going to forecast always going to predict in this method your future demands as your estimated level right now. So that's the reason why all the forecasts are the same. Now over here, these values, what they give you is the lower limit and the lower bound and upper bound of the of a confidence interval for the forecasts. And that's because when you make a forecast, you can compute you can compute the confidence level, the confidence interval, to have sort of an idea of how accurate is your actual forecast. Because you can always make a forecast, you can always make a prediction, but if you have no notion of how accurate it is, then it's not really very useful at all. So for instance, if I say, okay, I predict that, let's say, okay, let's maybe make a slightly exaggerated scenario. If a missile is going to arrive here in the US, and they say, okay, I predict it's going to land, let's say, here in Troy, then that statement is not very useful unless I also give you some information regarding how accurate my prediction is. So if I say, okay, so I predict it's going to land here, or more or less, so here, or some radius of, let's say, 1,000 miles. So 1,000 miles is a long, it has is a lot of uncertainty. So my prediction is not really very useful at all. So that's kind of why we're interested in the kind of for the same reason where we are interested in the confidence intervals, to sort of quantify how sure we are, how confident we are in a specific prediction. So for instance, if we want a 80% confidence level for our prediction, then we have this interval from 48 to 87. So the actual prediction is this, but we are sort of 80% sure that it is over here. And if you recall from your probability and statistics, this does not actually mean that the probability that the forecast is actually here is 80%. It's a little bit more subtle than that, but that's not a completely unreasonable way to sort of informally think about it. And here you have a 95% confidence interval. So the more confident you want to be, sort of the less useful the actual interval becomes, because here, as you can see, the interval becomes wider. So the lower bound becomes smaller, so it goes from 48 to 37, and the upper one goes from 87 to 97. So the more certain you want to be, the kind of wider the interval is going to become, until it eventually becomes kind of useless. So here, this command, it gives you the 80% and 95% confidence intervals, which I think you will need for your homework. Okay. Now we have all of this. Now let's plot this forecasts. And as you can see, so the next 8 forecasts are always the same, as you can see over here. And what this over here is doing, this kind of darker gray blue region corresponds to the 80% confidence interval for the predictions over here, while the gray one corresponds to the 95% confidence interval. So over in the gray one, we are in an informal sense, we are 95% sure that our prediction is correct. And if we want to be a little bit, we want to have a more precise sort of interval, so a less wide one, then our confidence level needs to decrease to 80 and so on. Okay. So now, as before, since this is a relatively simple method, the simple exponential smoothing, we're going to see briefly how to implement it in R manually without depending on packages. So let's see. Let's let's write manual version of simple exponential method. Again, D will be our dataset kings. We're going to need some alpha, and we're going to talk about how to manually compute the optimal value for alpha. Let's see, for now, let's fix it to 0.4. And we're going to need also some L0, which before we used the D1, so we're going to use that again. So your initial demand, so your first demand, I mean. And okay, we're going to construct as before. We're going to iteratively construct L. So we're going to use a for. This time we can start in 1, because why not? And okay, so let's see. We're going to use this expression over here, and there's only the small caveat. Then when t is equal to 1, then we need L1 to be a convex combination of D1 and L0. So we need to be a little bit careful and use, at least this is the simpler way I can think of. LT should be alpha of dt. So here LT is actually just L1 and dt is actually just L1, D1 I mean, because t, this is the case where t is 1, plus 1 minus alpha of L0. Okay, now I'm going to copy this, and if this is not true, so if t is greater than 1, then kind of the same formula is valid, except now LT is replaced by LT minus 1. Okay, and now we have L, and yeah, let's run it. Okay, let's run it, and we have L over here, and let's now compute the forecasts, which is very similar as before. So the initial forecast is actually, now we do have an initial forecast, is L0. So this is F1 equals L0. And then we have just the same L from 1 to the length of your data set minus 1. Okay, so let's run this. So these are our forecasts. And we can, like same as before, we can plot them both at the same time. So let me open just to copy the previous moving average. Yes, and you have those both over here. So you have your data set in black and your forecasted values. Okay. So I hope this was useful. Actually, no, let me do, or I forgot. Let's also talk about how to compute the optimal value of alpha, because here alpha was fixed to 0.4, but let's actually see how to compute the optimal value for alpha. So, I mean, we can use some of the several numerical optimization functions in R, but let's sort of do it in a more manual way. So actually what I'm going to do is, so first here, note that the sum of square error, so minimizing the mean square error is really the same as minimizing the sum of square errors. And the sum of square errors is really just sum of your forecasts minus your actual demand. You take the square and you sum everything, and this is your sum of square errors. So in this case, is this for this particular alpha. So I'm going to copy this code, and I'm going to create a function, so a function of alpha, with the output being the sum of square errors. And then I'm going to use that function and minimize it. So let's see. So let's call it, actually let's call it SSE function alpha, and here I'm gonna paste the previous stuff. So I don't need this part. This doesn't make sense now. We can leave this, it's fine. Okay, so we have all of this, and this should be the output. So I don't need SSE. I just need this to be the output. So we have now a function that the argument is alpha, and it's going to give you the sum of square errors for that specific alpha. So I'm going to run it, and I'm gonna test it. So first, let me run this. So for alpha equals 0.4, this is the sum of square errors. And now if I call the function SSE at alpha 0.4, then I get the same value. If instead alpha was 0.2, let's say, then I would obtain this value, which is actually a little bit better than the previous one. Okay, so now I have a function in alpha of the sum of square errors. So I can do maybe, let's say, alpha to be a sequence from 0 to 1, jumping sort of from 0.05 to 0.05, and then let's call this SSE alphas. Actually, let's call this alphas, not to confuse it with the previous alpha. And this should be so this is not a vector function, so I need to do a for loop. So let's do this. Let's make it first an empty vector, and then do for k in 1 till the length of alphas, SSE alphas. I'm going to add the value of the SSE at alpha, at the kth value of alphas in this sequence. Okay, so I have this, and so I have now a sequence of the different values of the SSE for different values of alpha, and now I'm going to plot the alphas and the SSE alphas at the same time, and let's make it a type O, so that's a little bit easier to see. SSE alphas, did I do wrong? Okay, I probably wrote one of those wrong. So as you can see now, you have the sum of square errors as a function of alpha, and you see that the alpha that minimizes the sum of square errors, which again is the same as minimizing the mean square error, is going to be roughly somewhere around over here. So something like 0.25 or something like that. So we can be maybe a little bit more precise, and let's make the sequence instead from, let's say, from 0.2 to 0.4, and let's make the steps a little bit smaller. Let's run this. So the optimal value should be from 0.25 to 0.30. Let's run this. So let's say the minimum value is somewhere around 0.27, and let's actually compare this with sort of the optimal value obtained by the Holt-Winters function, which is actually, it's close enough. It's 0.2689, so it's close enough to our sort of intuitive, informal way of finding the optimal value of alpha, so it's close enough. Okay, so I hope this was useful, and thank you.